Okay, continuing on to section 17. So we've got A closed in Y closed in X. Show that A is closed in X. Well, we have Y minus A is open in Y, and X minus Y is open in X by the definition of closed. So Y minus A equals Y union intersected U some open U in X. And so X minus A is X minus Y union Y minus A. Okay, so X minus Y union Y minus A is Y intersected U. Um, and so we sort of put that inside. So we'll get X minus Y union U intersected X minus Y union Y. That's distributing that out. And so that equals X minus Y union with U, right? Because X minus Y union Y is just X, and X, this set here is contained within inside X. But this is the union of two open sets. So X minus A is open, so that means A is closed. Okay, question 4. We've got U open in X, A closed in X. I want to show that U minus A is open in X and A minus U is closed in X. Well, U minus A then is equal to X minus A intersected U, which is the intersection of open sets. So that shows straight away that U minus A is open. And A minus U is X minus U intersected A. And this is the intersection of closed sets. So A minus U itself is closed in X. So that's pretty straightforward. Okay, so now we want to show that the closure of the open interval is contained within the closed interval. Right, well, let's argue a little bit by contradiction by saying, well, let's assume we have an element which is not in the closed interval AB. So that means either C is less than A or C is greater than B. Let's just look at the case where C is less than A. The case for C greater than B is just the same. You just replace, do the same argument, but just replace minimum by maximums and less thans by greater thans. Okay, so, well, if C is minimal element, so that means then that CA will be an open set not meeting the open interval AB. So that means C can't be in the closure of the open interval. And if C is not minimal, then there exists a D less than C. And so then the open interval DA is an open set not meeting AB and containing C. So again, C is not in the closure. So if C is not in that closed interval AB, we've got that C can't be in the closure of AB. So that shows that this is contained within in that closed interval. So there are kind of like four possibilities then for the closure of AB. It can be closed interval, or it could be half open interval, or it could be just itself. So which one of these is going to be in it? Well, how can A not be in the closure of that open interval? So that means there'd have to exist a C. This would be if and only if there's a C greater than A and interval AC is empty. For then, in that case, then A and then whatever's here is going to be the same thing as the closed interval. You can just replace the open interval at A with the closed interval at C. And you can ask the same thing about, well, when is B not going to be in the closure? That's going to be in the case when there's a D less than B and that interval DB is empty, because in that case here you can then replace B and whatever here by a closed interval at D. So this is true, equality true, is if and only if A has no immediate successor and B has no immediate predecessor in the order. Okay, so for example, like in Z plus, okay, because then, for example, the closure of 1, 2, well, actually that's just going to be the empty set, right? Because there's no integers between 1 and 2. Okay. Okay, let's show that the closure of the union equals the union of the closure. This way is easy because if A is contained in A union B, then A closure is contained within that closure, and it's the same for B. So B closure is in that. So straight away we have that the union of the closures is contained within the closure of the unions. And going the other way is also straightforward, is, well, A union B is A closure union B closure is a closed set containing A union B. So therefore has to contain closure of A union B by the definition of closure. Because remember, the closure of A union B is the smallest closed set containing A and B. Okay. What about the other way? So this for C, this kind of holds because if A, right, is contained within the union, then that's also going to be true for the closures. So this thing, so this set here is going to contain all these guys. So in particular, it's going to contain its union. But equality can fail. For example, just let look at the union of AX, where X is just an element of 0, 1. And so an AX is just the singleton set X. So the union of all the singletons is 0, 1 itself, right? And the closure of that is equal to the unit interval. But of course, the closure of a singleton is just itself. And so the union of the closures is still going to be just 0, 1 open interval. Okay, 8a. The proof is kind of like what we saw before. The intersection of those closed sets is going to contain that closure because, again, the intersection of closed sets is closed set, and it contains A intersected B. So by the definition of closure, that's got to be true. But direction the other way need not hold. For example, if A equals 0, 1, and B equals 1, 2, then the intersection of the closures is just going to be the set 1, the singleton 1. But if we look at A intersected B, that's empty, and so if we look at its closure, that's also going to be a thing. For the arbitrary intersections, the argument for A is basically still going to hold. So the intersection of all these guys here is going to contain these things here by sort of the same argument as before, and this argument also shows that the reverse inequality cannot possibly hold. So what about C? Well, we can have closure of A minus the closure of B does not necessarily contain A minus B closure. For example, if we look at A equal the closed interval 0, 1 and B equal the open interval 0, 1, right? Then A minus B is just the points, the endpoints 0, 1. So the closure of that is the singleton 0, 1, but the closure of B is A itself. So A minus A is empty. So that can hold. But it's always going to be the case that A minus B is going to contain that. Because if you've got a neighborhood X, if we have an element of A minus B, if it's not, X is not in the closure of A minus B, that means there exists a neighborhood U of X with such that U intersected with A minus B is the empty set. But if X was in the closure of A, then U intersected A would not be empty. So U intersected with B would be non-empty because we'd have to cancel out. So if X is in closure of A, X would have to be in the closure of B. And so X would not be in A closure minus B closure. So if anything is not in here, it can't be in there. So that means if X is in there, it has to be in there.